Today, can you tell us about Dirac lattices?
So first I want to apologize for very misleading name. Actually, different type of Dirac lattices, which I will talk. And I'm a bit nervous because actually this is based on a work in progress still. So there is no paper. So to come to this talk, I had to put together many disjoint pieces which are not yet, do not yet exist as a single paper. However, there are a couple of related papers. Yeah, so today we are speaking about religion. So in this context, I would say that this work aims to bring sections of the God. Okay, but let's go and okay. First, I will give you a sort of motivation, but this is very shaky region, a very shaky part of my talk, and I will be grateful if you will try to bust it completely. So. So you're welcome. I will enjoy the challenge. So first, okay, to state the problem. Yeah, another thing which to prepare for this talk, of course I didn't have slides until today, so I finished them writing just today before my talk. I gradually gave up all technical details, so my talk, I think, became a little bit philosophical, theological, yeah? So, let me start from the very beginning. So we know that all models, okay, we start with no discussion, any high energy physics model, any QFT model, they're based on Lorentz symmetry. And we know that Lorentz symmetry giving us a lot of headache. Starting from the fact that Lorentz group is indefinite, okay, it's not a compact group, and also it's okay. First of all, it's a Lie group, so it's a continuous group. So we always face the problem of UV divergences. Even worse is in gravity, because in gravity it's supposed to be the local symmetry, the local gauge group. Of course, this is based on very solid ground, observational ground. So we don't see any sign of violation of Lorentz symmetry, Lorentz invariance, apart from the, what is the name of that experiment a couple of years ago, which appeared to be a completely fake problem. Yeah. Already forgot.
A neutrino experiment?
Neutrino experiment, yeah, they found a violation of causality. But, okay, must it be indeed an exact symmetry? Okay, we don't want this to be true, actually, and come back to Penrose's arguments back in the 70s. So what he said, he came to a purely logical conclusion that concept based on continuous space, a Lorentz symmetry, is faulty if you consider quantum gravity. And the reason, his argument was that in 1 cubic centimeter, you cannot have the same number of degrees of freedom as in, let's say, the volume of the solar system or the volume of the galaxy. So, but if you assume the continuum, continuous space-time, actually, you have to admit this fact. So, and he points that this is the root, actually, of difficulties in quantum gravity. So, by the way, he started from this point and proposed so-called spin-form models, and actually that was the, okay, he needed an object to effectively describe these systems of spins, and that's how he invented twistors. Yeah? So twistors comes from attempt to describe these spin systems. Okay, we met already. Okay, from time to time there are splashes of proposals to describe Lorentz symmetry in a framework in which is an effective symmetry. Maybe last noted, that's what not so far ago, 2008, 2009 by Horava, when he proposed that Lorentz symmetry is an effective symmetry of a system at the infrared or Lipschitz point. So actually, this is very tempting idea because Lorentz symmetry indeed looks like, okay, Lorentz group looks like a conformal group for system in a dimension less. So you may be tempted to produce a system in which you have a critical point and the Lorentz symmetric description emerges at this critical point. Okay, so on the other hand, we have good, nice examples already mentioned, I think by Diego. In condensed matter, we have systems like graphene, topological insulators, and other guys which have linear dispersion relations. And okay, what is common in these systems is that you have Fermi surface which degenerates to just a single point in momentum space. Okay, of course there are different problems related to this system, like that they are strongly correlated, but apart from this, you have this interesting common feature. So, and dispersion relations are linear and non-degenerate, and it appears that mathematically there are not too many possibilities for having linear and non-degenerate spectrum. And all these possibilities were classified in, okay, now monumental work of Atiyah, Bott, and Shapiro, okay, mathematical work, of course. So then, in this case, you inevitably end up with a collection of wild fermions. So, and this is interesting. This might, okay, so to quote I think John Schwartz 2 years ago at String Conference, we should not believe in coincidences, right? So if something coincides, that should be some reason behind. At least we should always try to find.
Take coincidence is serious.
Oh, okay, thank you, yeah. So, okay, we should at least try to find why so there, okay, I hope I try to point you that there's a number of coincidences. So Lorentz symmetry is such a, okay, sticky guy which emerges in, you know, a very basic situation when you have linear non-degenerate spectrum.
But in those cases, we see the leading irrelevant corrections breaking the symmetry. Because it's not
Okay, yeah, for example, if okay, this is a very simple argument. If the Fermi surface is not point-like, you have to take the average over, let's say, over the surface. Then, this case, linear term will not survive. So the leading correction will be the leading term in the dispersion relations will become quadratic, right? So that's why this relation between point-like and linearity.
No, but even close to the formulation, even if you're not in graphene, even if you have a linear spectrum, you see corrections to the spectrum.
Yeah, okay. There is another point that you have. Yeah, this also is related to a Bott-Shapiro construction. And, okay, this Horava pointed out this relation to stability of linear spectrum. So, in some situations, you have this spectrum stable against such corrections. And this is related to non-trivial to existence of some non-trivial topological charges. So, but as Horava pointed, actually these Fermi surfaces, they are parameterized by K-theory charges. So, an existence of non-trivial K-theory charges results in stability of the surface. So, you cannot break them by small perturbations. You need large perturbations only. Okay, so yeah, as you see, so far no equation, so only philosophy. So we know actually from different areas of, including string theory, that actually Fermi systems are quite nice to when you have to deal with geometry. So completely unrelated fact is that you can encode some, okay, not some, but practically all ADS CFT geometries in terms of Fermi, okay, in terms of Fermi states. This comes back to Lin and Maldacena, 2004, right? Yeah, and as I already pointed, actually the Fermi surfaces are naturally classified in terms of K-theory. So this is a little bit less known paper by Kojava in 2005. So, and again, I said already, yeah, I'm not following my slides, so I'm going a little bit ahead, always. So, as soon as fermionic spectrum is linear and non-degenerate, these wild fermions and corresponding to them, or Dirac fermions corresponding to them, Lorentz symmetry will always emerge. So this conclusion you can come to based on a Thiabout and Shapiro construction, and actually classification. I would call it better classification rather than construction. So they describe all possibilities in relation between. So what is typical for these models and what can be generalized? Okay, I call Dirac lattice generalization of this to arbitrary dimension. So in this model, okay, Dirac lattice, we have a Fermi particle which is hopping on a graph, which is specified by adjacent symmetrics T, so which is the main variable in this description. So this model is, of course, non-relativistic. We have an absolute time, which is dynamical parameter, so we have dynamics. It's a dynamical model. Then, when you analyze this adjacency matrix, you find that there are some special cases, and these cases you identify by some, okay, it reduces to some algebraic equation on T, which guarantees you, which is equivalent to emergence of linear dispersion relations in infrared, and respectively with emergence of Dirac fermions or collection of wild fermions. But you have a constraint here that the number of positive chirality equal to the number of negative chirality fermions. So people who is familiar with the lattice may see this as an analog of doubling, lattice doubling phenomenon. So in all this model we have absolute time, which exists from very beginning, but special geometry is inherited from the graph. So it's inherited in, not in a direct way, it's a bit in a spectral way. So, but as a result, they merge into a Lorentz symmetric system. Furthermore, you can see that if you deform this graph, so you go away from T, which results in a Dirac fermion, by some small deformations, the resulting theory will appear to be, the resulting fermion will appear to be coupled to some gauge field, a Yukawa, at least in 2 dimensions. In more than 2 dimensions, in higher dimensions, there will be also spin coupling, and perhaps also some form fields, which, okay, you have to deal with. So, but still, this situation doesn't make me too happy. So, why? Because we have to start with a system which has an absolute time. So the time is external and put from very beginning. What if to try to generate the time itself through this matrix, or through this graph approach? So that would be one-step generalization. So of course, we have no time, so we have no dynamics from very beginning, so we should start with some statistical model, some random fermion distribution on a graph. But the problem is that we have no time, no Hamiltonian, no energy levels, no Fermi C, no Fermi surface. So we have to find find a replacement for this. Now I came to most shaky part of my arguments. So, okay, let's try to do with Wick rotation. We know that in a Wick rotated theory, the action, if you start a theory, relativistic theory, and look at the action and you do a Wick rotation, the action will become something like energy. So then you also can trace that semi-classical or saddle point approximation will be some, okay, mapped to low energy approximation in this new energy. Then you have this hierarchy of energy levels, and then you know that how you have to proceed with a fermionic particle. You have to fill the C up to the surface, and then low energy modes are splashed on this Fermi C, or this surface. Everything is fine with this, it should work, perhaps. The only problem is that when you do so, when you deal with particular systems, mostly first order systems, you may end up with Hamiltonian that will not be Hermitian anymore. Okay, this is a bad thing, which I don't know what to do, but okay, so far, okay, let's call the Fermi surfaces which you obtain in this strange way as pseudo Fermi surfaces, because they don't really exist. But I need just one thing from them. I need just surface. So I don't care whether there is any C below the surface. So now let's go to my model. Oh, I still have to remove more. Sorry, there is one equation. So just start to look at this statistical sum. Of course, we know from Neumann and Wiener that it makes no sense because of this IS. Okay, at least it makes no sense in the case of bosonic integrals. For fermionic integrals, we use Grassmann. But anyway, to give sense to this statistical sum, we know that we should do some analytic continuation, and this analytic continuation, okay, can be in easiest way performed by Wick rotation. So that's why I choose this sort of statistical sum. And the action is very simple. It's just I have a fermionic particle which interacts through some adjacency matrix. And this matrix describes some graph which could be of whatever origin, maybe just some set of eigenstates and distribution of fermionic particles, or distribution of some signal satisfying Fermi statistic through this set of eigenvalues. But of course I don't take, okay, I cannot take generic type of adjacency, but I take one which possesses translational symmetry. I need this badly, at least for beginning. So if there is a translational symmetry, also T, unfortunately here, and Ti, they are completely different objects. So T is my adjacency matrix. I can expand it in terms of translational operators. Ti are translational operators. Then of course this expansion goes to the power which is as large as the size of my graph. Maybe if my graph is infinite, it should go to infinity, but I will not look at generic case. I will cut it just to nearest neighbor coupling of these graphs. So I will look at types of adjacencies which are very local in this sense. So also, I planned to remove this line here. Sorry. Okay, this is a kind of mess I wanted to convey you. So my adjacency matrix, my graph from above looks like a lattice. But if I take a close look of this point, I zoom it. So here inside I have generic graph, arbitrary graph. So every line represents a matrix element which connects sides of the graph. It could be generic. Then every side of this graph is connected to arbitrary side of neighbor graphs. So, but then all this structure is forming a lattice, okay, which is periodic lattice. A periodic lattice I need to be able to introduce a Fourier transform. So also I was very ambitious from very beginning, but now I want to be humble. So I want to look at the simplest case when this internal space, this internal graph is just consisting of two sides. Very simple case. And as you start analyzing it, you immediately realize that this internal space can be described, it's described in terms of four-dimensional Clifford algebra. So, and actually you see this through the relations given to you by ABS classification, ABS construction. So, therefore, I will assume from very beginning that my internal space is consisting of two sides and my translational symmetry is four-dimensional, not to run into a mess, because otherwise, actually, I will run into a mess. So either I will have no solution or I will have too many solutions. So generalization is sort of straightforward, but technical. So now I can go to the momentum space, and in the momentum space, of course, everything becomes just matrix in the internal space. Okay, call graph, the small graph in the sphere, I call internal space. I can expand, of course, you know that any 2 by 2 matrix you can expand in terms in the extended set of Pauli matrices. So, where you extend it by adding just unit matrix sigma 0. So, and I can write this, okay, finesse matter people call this energy matrix, but this is not really energy. Lattice people call it fermionic matrix. Better to call it fermionic matrix because it's more like sort of action rather than energy. So, of course, apart from the shaky argument with the pseudo Fermi C and pseudo Fermi levels filled with something strange, if I want to stay on the surface, which the pseudo surface, the contribution to not low energy, but to semi-classical action, to stationary phase action, will be given by states, okay, call me state configurations near zero modes of the adjacency matrix. So I can write the zero mode condition as the determinant equal 0 in terms of the extended Pauli set basis, and this looks very interesting, very familiar. This looks like Lorentz interval equals to 0. So of course there is not a point to this, not a point solution, but rather we know it's a conical solution. So, but if I do a Wick rotation at this stage, it's clear that this sign will become minus as well. So then the only solution after Wick rotation is just the tip of this cone. So that's the only reason actually I need to do this Wick rotation. Just because in this case I have a clear criteria for this point, which I call pseudo Fermi points, because they're not really Fermi points. I cannot associate any Fermi C to that. Okay, unless I do some strange manipulations. Okay. So then, as soon as we did this, all the stuff works. So yeah, it looks like broken phrase. So if this will be non-degenerate, linearly non-degenerate, it fluctuates. Okay, the fluctuations around this point actually produce me a Weil fermion. To say here. Okay, so let me summarize it. Pseudo-Fermi point is a solution to this equation. But now we can ask the question for which adjacency matrices such solution exists and how many of them exist. So existence is not very difficult to prove as soon as we know location of at least one Fermi point. Is the consistency is just we put this to 0 at this Fermi point. So then this will define us this coefficients of expansion alpha A in terms of remaining alpha AI and in terms of location of these Fermi points. But the question, how many points? Is it the only solution? The answer is definitely no. There are many. Okay, there should be at least another one. So another thing which I have to specify is that is this an isolated solution or it could be just a part of, let's say, a line of Fermi points. Maybe you have a Fermi line. Fortunately, for the last question, I have a definite answer in terms of topology. So at least for the case of 4 dimensions, I know that I can define a topological charge. And if this charge, and this charge is measuring the class, homotopy class of map of, say, small sphere in the K space to the sphere, to small sphere in the space of, okay, this matrix space in the, okay, Wick rotated basis. And we know that this group is non-trivial, it's Z. So if I take actually a solution with non-zero topological charge for given, let's say, singularity, I'm guaranteed to have the right spectrum. Moreover, I know that since my Brillouin zone is compact and I have periodic boundary conditions, sum over all such topological charges should vanish, so flux should be 0, total flux should be 0. So means that the total charge for the Brillouin zone should be 0. Now what does it mean? So if I have this topological charge plus 1, just analysis show you that in the low energy limit you get a Weil fermion. If you have positive chirality, if you have -1, you get a negative chirality. Okay, if you n is larger than 1 magnitude, you get a bunch, a multiplet of either positive or negative, it depends on the sign of n, chirality fermions. Now let me go quickly. Of course, if you take small, okay, fluctuations around these points, you quickly end up with a Weil fermion, Weil fermionic action. So which I cheated you. I put some technical details, but very little. So okay, I am speaking mostly about the minimal setup where we get one. Yeah, I forgot to. Yeah. So one important thing is that even if we start with just one pseudo-Fermi point, somewhere in the Brillouin zone, we have, in the first Brillouin zone, we have also the second one. So we always have a pair. So in this case, we end up with one positive chirality fermion, one negative chirality fermion, and okay, which is Dirac fermion. In general, you can get quite different set of U1 group, maybe not only UN, but I didn't think so far. But okay, now what happens I deform this graph from the status of being Dirac lattice, I can go to adjacency, which is different from Dirac lattice adjacency by some small deformation. So it means that I am, for example, I break through the translational invariance. I make generally deform the graph. So as a result, again, it's a purely technical. You can see that in low energy, this will be mapped into the replacement of the free Dirac particle to Dirac particle coupled to various fields, among which there will be spin, connection, and gauge field. Also some scalar fields as well. So, okay, so I think it's enough. Let me conclude by reminding that we consider a Fermi particle on a graph, and the graph is parameterized by the adjacency matrix. So with translational invariance, model describes a Dirac particle or a collection of particles, not necessarily a Dirac particle, in the infrared limit. Yeah, and I forgot to say this, but it happens at a generic point of parameter space defining the graph. Generic point means that this description remains stable whether I deform the parameters in the class which I described, so arbitrary small deformation. So the particle spectrum depends on zeros of adjacency matrix, and this is a generic point. Graph deformations, more general graph deformations, actually almost wild graph deformations, but which, let's say, don't spoil the asymptotic value, so which decrease quickly enough when you separate. So which are the only restriction is locality. They lead to gravity fields, gravity and gauge field, and also scalar fields coupled to this particle. Also, now this speculative part comes that back reaction from fermions is expected to produce dynamical parts for this gauge and gravity fields, similar to what people call sometimes Sakharov mechanism. Okay. So, of course, it's interesting to study graphs which are leading to realistic quantum field theory models like QCD or standard model, but of course it's a lot of work to do this. Not sure I will do it. But okay, this is in the hope that this approach brings us to some fundamental theory. But what is its failure? And there is no it's not fundamental theory. Then we have a backup. Then we can sell this to lattice people, and they can use it for lattice simulations. So then there's definitely a motivation to continue to work on this, better understand the discrete systems which generate, which bring us to gauge theories. So sorry for keeping you over the end time. Thank you for your attention.
Any questions? So, other people like in quantum gravity, like
Please speak louder.
other people from quantum gravity have looked at similar things, use random lattices.
Yeah.
And how is that related?
Okay, the word lattice is common, but
Graphs, actually.
graphs.
It's like
Okay, this is not a lattice. So people mostly look at, most naive thing is triangulation, right? So, but in this case, it's not a triangulation. It's more like spectral description. So I would say it's related to, more or less, to Kahn's approach to non-commutative geometry. There's definitely a relation. I think there's one-to-one correspondence between graph and non-commutative geometry. So, It's a little bit different than, it's not a triangulation. There is no space existing before, so.
Any other questions? If not, let's thank the speaker again.